Hello everyone, welcome to VLSI Path. This is part of our static timing analysis series, guiding you from basics to advanced concepts step by step. Today we are going to discuss what is timing analysis. So let's dive in.
What is timing analysis? Whenever you are going to a market to buy a product, what will be your first check? Like if I provide the input, after how much time it should generate the output, right? So that's what we call the timing or the frequency. So you are going to market to buy a phone and then you will check, okay, what is the frequency at which it will operate. So if you are saying frequency, so you know the delay is equals to 1 by frequency. So there the time is after applying the input, what will be the minimum time our device will take to generate the output. That's the time delay we say. And here which in the timing analysis, we check for the when we are selling a product, we give client a number that this product will operate on this frequency. So timing analysis is something which is to verify or validate like whether our design is working correctly at that desired clock frequency or not. Or if let's suppose you have given a number like 1 gigahertz, this will be the frequency of my device, it will work. But what we will do as an engineer, we will try to optimize that time also. Like, is it possible to maximize this frequency? Is there any possibility in that design where we can reduce the delay somehow? That's all comes under the timing analysis. There are two types of timing analysis. First one is STA, second one is the DTA. STA is static timing analysis. Static meaning we are not going to use any input test vectors for this. So we have the design, we know all the routing and all the cells delay, we know the net delay, but we do not know when this will be the input, then what will be the output, meaning the functionality check. In the VLSI design flow, we already have checked the functionality in different stage, but here we are not going to check the functionality. We will take all the delays of the net and cells, there we'll check the critical path that has the maximum delay. Okay, excluding the false path and multi-cycle path. We will discuss those things later. So in the STA, no input stimulus required, meaning all the analysis will be on the given net delay, cell delay we will consider irrespective of the input stage. From the given design, we will take those delay, perform the analysis, try to optimize the delay on those particular cells. In the DTA, we provide the stimulus. Stimulus meaning we will provide the input test vectors and corresponds to that input, what will be the output. There we will check the functionality. And when we have provided the input, so corresponding to that input, what will be the delay of that path. So what will happen? Let's suppose you have a design where if you give 100 as an input, it is taking a different path. Let's suppose you have muxes in between or other combination of equipment in such a way, it will take the longer path. But when you apply 010, it is not taking that path. So for this 010, critical path is some other path. So we do not have to optimize or check that particular path which we were getting in 100. So that is how, with respect to the input stimulus, we check the functionality and timing both in the DTA. So we try to optimize the overall design. Now, as I discussed in the STA, irrespective of the input test vector, it will check the critical path that has the maximum delay. Then it check the violation on all the paths, but try to optimize the delay of the worst case scenarios. Okay. And in the DTA, it validates the timing by observing signal transition. So as I said, when we apply the test vector 100 or 010, so in respect to that input test vector, what will be the output, which path it is taking, what will be the rise and fall time of those particular cells, which it is taking for that particular test vector. So this will be tested in the DTA. Now STA, as you will thinking like, why are we going for the STA? If DTA is that good, then what's the need of the STA? So DTA, it is obviously give the exact values, but the problem is it is very complex and we cannot perform DTA for the last design. So in today's designs, we are having like billions of gates, right? So having the test vectors, the input test vector in such a way which will cover all the input sets, and then optimize the delay for those, it's like it will take years of years, and we do not have that much time. So STA is a good choice for the complex design, which are large design, and DTA is good for the small designs like the IPs, where we can perform this. Although ST is also very complex, as the designs are getting more complex and with number of gates or devices transistors are increasing, devices are getting complex. So ST is also a very critical process to identify the violations or then optimize them. But DT is like next to impossible to perform on these complex circuitry. Now, in the STA, it cannot identify false path and multi-cycle path. What are these false path and multi-cycle path? We will discuss in the next slides, but it cannot identify by soon. And the DTA, it can identify false and multi-cycle path. Now, maybe some of you are thinking that in the STA, we check the false path and multi-cycle path. Why I'm saying it cannot identify. The reason is STA, we are not using any input, and false path and multi-cycle path, we check with respect to input test vectors. So in the STA, we cannot identify, but we define in a separate file. Like this will be the false path, this will be the multi-cycle path. We define in SDC file, and then the analysis will exclude these false path and multi-cycle path. That's how it will take care of these paths. But if we do not define in the SDC file, then it will not be able to identify false path and multi-cycle path.
That's all for this video. See you in the next video. Thanks a lot for watching.